take this opportunity to let you know that this day, the one they have this week conference open an activity throughout the semester with more activities in November and the combination in December when actually will be visiting us here, hopefully for more than a week, on generalized Keller and also Keller geometries. And so the opening belongs to one of the organizers. So this activity, Lino Grama from UNICAMP, is going to tell us about spherical T-duality.
Okay. It's very nice back here. I mean, it's a very nice place. And I would like to take this opportunity to thank you for Professor Ludmil Cocycle to create INSA and to give the academic guidance to INSA. Yeah, but I guess the most important, believe in INSA, to take this initiative and go this work very hard. And thank you so much. And the title of this talk, this is Spherical T-duality meet exotic spheres and the Homotopy Hopf Manifolds. This is just a report of this work in progress joined with Ludmil Cocycle and Leo Cavenaghi. And this is a part of the program, more big project, and just to take some general picture. And the next talk we give by Leonardo probably will put some more details in the picture. And actually, after attending the lecture from Professor Carlos Aragon on the Wednesday, I realized maybe the title most correct will be symmetry and duality, just this. And but I keep this title in the website. And just to recall briefly, what is the T-duality in the usual sense? Okay, and T-duality is for the work in the very important work in the Stronger Zaslow. They give an approach to mirror symmetry. This is a paper in the 1996 in the Nuclear Physics B journal, and the title is Mirror Symmetry is T-duality. The title just explained, self-explained. And what is the, just for short, SYZ approach to mirror symmetry? We start with the mirror pair of the Calabi-Alves, and we consider special Lagrangian vibrations, pi and y hat, over the same base, and the x and the x hat will be dual if this vibration has the torus fiber will dual one of you. Is a dual torus. And as a consequence, the Lagrangian section of mu should correspond to holomorphic line bundles on X hat. Of course, this is a huge simplification of this history, but this is the philosophy. And the philosophy will be you have some torus vibration, and the duality will happen if you have some dual torus on the fiber. Okay. And that is a little bit, is also T-duality, but it's Bognet, Hamabus, and Matai in the 2004 in a paper in Communication Mathematical Physics. Introduce another kind of the T-duality is a T-duality for principal torus bundle with equipped with the H-flux. This is a proposal for these three mathematicians, physicists. Will be some model for the string theory, etc. Okay. And in the sequence, that is they wrote a series of papers and the proof K-theory for this approach, and a lot of topological properties of this approach. There is some twisted cohomology, etc., etc. There is a sequence of papers, and the intuition behind this idea is we have two torus vibration, and that this torus vibration will interchange the topological charge there's a curvature of the bundle or second chair class, and these three forms in the other side, the H flux. This is the most intuitive, and the vice versa. Because in this case, the duality occur in a pairs. You need a manifold, comma, not three form, not flux. And the flux, we can understand this like a germ. You can twist the bundle. You can put it this form and produce a germ. And in the picture for this duality in the sense of the Hannibal, Bognet, and Matai, we start with the torus vibration, E, H, over the same base, N. Okay, and how we say this, the duality occurs? The duality will happen if you have some pullback for the projection P from the three form H in the one side, and we have the projection P hatch, I'm sorry, P check in the mirror, in the dual, and then we pull back the T2 forms, and then we consider the product space. It's a fiber bond over the base M also, and we declare this pair is a T-dual if this three form on the big space is exact. Okay. And then, okay, at the Lie algebra level in the torus, this will mix this fiber, okay, and also other people realize this will produce some effects of in the structure, the geometric structure involved in this construction. Okay. And then we just ask this some technical, maybe here. Can you see the hand, right? Maybe we just need to ask for this F will be some kind of the curvature also in the invariant by this 2T2M torus invariant form. This is the usual T-duality in the sense of Bognet, Hannibal, and Matai. And there is also application, this is interest for us. There is application between T-duality and the generalized complex geometry. This structure generalized complex. Here I just put enough phrase. This is of course is a topic, but generalized complex geometry was introduced by Hitching and developed by his student Michael Gautieri. And now another generalized complex structure is on an even dimensional manifold is a complex structure on the double tangent bundle. And a generalized complex structure has complex symplectic Poisson structure are particular things. This encompasses a lot of structure in one big structure, let's say. And for instance, Gil Cavalcanti and Michael Gautieri, they both are students from Hitching. That is made, they prove the compatibility of the generalized complex structure in T-duality. They can put this in the same package. And they prove that in some cases, this T-duality interchange complex and symplectic structure. Some are twisted by this H flux. But we can understand this like in a manifestation of the mirror symmetry in the sense they switch the complex symplectic structure, maybe in the same similar way as in the Strominger result. Joint with my colleague Bibiana Del Barco and Leonardo Soriani, we can extend this for the new manifolds, and we introduce this infinitesimal T-duality. Anafino e Adriano Tomasini and Bibiana and myself, we studied in different works and studied generalized G2 structure and T-duality is compatible also. Katsarkov and Soriani, they investigate coisotropic brains and T-duality on new manifolds. And more recently, Mateus Costa, Ludmil, myself, we investigate invariant structure on non-Kähler manifold. And here is a good example of this 3, 4 works is a consequence of the collaboration with UNICAMP. This is a very concrete example. And for instance, Matheus Costa was a PhD student in visiting Ludmil. Leonardo Soriani is also a PhD student visiting Ludmil. Viviana Del Barco is an Argentina from Rosario, now is in Campinas, but the whole package of ideas is circulated here, because here is like in December, January is a mecca of people go here. And now we goes to the main topic. The first main topic of my talk is a spherical T-duality. And this is a very similar concept, but instead we consider torus fiber, we consider S3 fiber or SU2 fiber. And this is a sequence of papers of Ognet, Egli, and Matai. And we start with the S3 bundle. And then now our H flux will be elementing H7 in the 7th cohomology. And the dual will be another fiber and another S3 bundle. And this is also the philosophy is the same. They interchange the second chain class and the H flux. But now we need to be a little bit more careful here, because the 1 and 7 form and the other is 2 forms, and we need to make some compatibility here. I will explain in a second. But the picture looks like the same. And we consider here this pullback of this 7 form in the product space, and make the diagram with commutative. And to fix this, this is already technical, just comment here, because we have this H flux is a 7 form, but in some cases we can use this DC exact sensing check homology to consider this as a 4 form. Okay? This is approved by Bognet, Egli, Matai. Actually, in our work, it's quite important because we are considered in this most cases the base is simply connected. In this case, we can not change, but we can encode the 7 form as a mesh in the 4 degree cohomology. But this will be important in a second. And this is as I just told you, we can relate this pair, and we can take this H flux, the image here, the push forward in the H4 by this exact sequence. And the question is whether we have this pair, we can build in a dual one. This is the dual question. And for now, we just for this most part of this talk, we consider the base as S4. And we consider the correspondence between this S3 bundle and the H4 given by the second chair class on the associate bundle. And we have this H4 of S4 is isomorphic to Z, and any principal bundle, S3 principal bundle, is classified by the single integer. And we assume that exists a dual bundle. And as a consequence, we have some the existence, we have in H hat in a 7 form, such that this relation holds. We consider the interchange, the flux and the curvature. And this condition is determined up to an element of this 7 degree cohomology. And if you fix the null uniqueness of the H hat, it is usually imposing some constraint on this top form in the big space on the correspondence of P times P hat over N. And then we have some diagram is very similar to this T-duality, but we need to make some more credit for cohomology level. But it's a work, it's a setup, it's well established. And just to mention, and this is the very useful theorem that instituted the existence of the spherical dual. And we start with the S3 bundle, P, in the fix the second Chern class with the second Chern class, and we pick the H in a 7 form to be a H flux. Suppose that exists in a bundle P hat S3 bundle satisfies this. Okay, and then you have some existence in the unique theorem for the dual. But the unicity is a little bit tricky because we are assuming the basis as 4. And this is very well remarked in the papers of the second set of papers, because if the base is not simply connected, maybe you have some trouble with the unicity of this dual. But in our case, we restrict ourselves to S4. And another remark, that is the case of the principal bundle and non-principal bundle is a treated in the separate paper by these authors. But here for the presentation, just put the general picture, and it doesn't matter if it's principal or non-principal, everything is good. Okay, this is the setup, the basic setup. We have now the picture of the spherical duality. And now we start with some another ingredient here is the Miller manifolds. Okay, just to start to recall the definition of linear spherical bundle. Okay, we call a spherical bundle over B is linear if the orthogonal group is the structure group of this bundle. Okay, or equivalently, if the transition functions of the bundle take values in the orthogonal group here. Okay. And from the work of the topologists, we have some classification of we have a bijection between this set of linear bundle S k less 1 over SL is a classifying, and we are restricted to this case in the k is equal to L is equal to N is equal to 4, and in this case we have S3 bundle over S4, and the total space will be 7 dimensional. And in this case, our bundles are parameterized by Z plus Z. Okay, and for if you pick 2 integer numbers, we can produce a bundle with the S3 bundle over S4. 3. Bundle, we put this, we put M7. S4. For each pair of integers, I can build another bundle. This is the classification and in the literature, these appears are Miller bundles.
You don't really need an N there, right?
Exactly, yeah, it's a type. Yeah, sorry, the base, sorry. I just realized this this morning, but I cannot check. Sorry. Okay. And what is called the Miller construction? The Miller construction, we pick pairs of the integer, and each pair will correspond to an element of pi3 of SO4. And we can build some maps. T depends on n and n. So SC3 to SO4. And then this maps describe explicitly the isomorphism between this pi3 of SO4 and the Miller bundles. This is explicitly the function. This 8 is a quaternion, and just this conjugation with the degree m and n, and this is representing an element in the pi3 of SO4. And we define also functions f, and this will be the diffeomorphism from S3 cross S3 into itself, just given by this component x, and then the second is an action g on the left. Okay, and how we will look at these functions because we have two disks before, and they will glue the boundary S3 by this function. Okay, this is exactly how Milnor construction is actually. You pick two disks and glue this, but the gluing is given by some tricky function. Okay, this is as I told you, I consider D4 cross S3 union gluing by this function. Okay, and this is a manifold n comma n, depending on these integers, and this is gluing along this boundary. Okay, and this gives rise to total space of this Milnor boundary. At this point, maybe is not clear, but in a second I give another explanation about this factor. But for now, this is the sufficient at this moment. But I back it here in a second. And the key observation from Milnor is that the n comma n is homeomorphic to the 7 spheres if and only if m plus n is equal 1 or minus 1. But these spheres is not diffeomorphic when m is equal to 2. And we have some spheres that are homeomorphic to the 7 spheres, but not diffeomorphic. And the completed description of this combination of m and the work of the user. Okay, but this is the Milnor construction. This is called the Milnor construction of the Milnor boundary. Now let us keep m plus n to k, and if you consider k is equal to 1 for the Milnor remark, this manifold is always homeomorphic to S7. And Milnor introduced this lambda invariant, and this lambda invariant actually this number is obstruction to diffeomorphism of the 7 spheres. And in this case, if this lambda of the manifold is not equal to 0, the manifold is not diffeomorphic to the 7-dimensional spheres. And if we plug in our situation m plus n is equal to 1, the lambda invariant is just for m times n plus 1 mod 7. Okay, this is very useful to detect when manifold is homeomorphic but not diffeomorphic. And our first remark here, it is we can put this construction of Milnor in the language of the spherical duality. And actually they are spherical T-dual. This is we provide another construction of lot of the well-known factor, but we can go further and explore a little bit more. And we pick the Milnor bundle, principal or not, with the H flux is an integer because we are the H7 of this space is Z. Then we have this following diagram. In other words, we can produce some Milnor bundles is preserved by spherical T-duality. And as a consequence, we can produce exoticity by duality. We can produce exoticity of the Milnor sphere by this language of the T-duality or spherical T-duality. Okay. This is a remark. And just if m is equal to 1, this bundle m1,0 is isomorphic to the Hopf fibration. And then, of course, if you look, you have lots of symmetries here between these numbers. Okay, the number here will appear in the side, and this is a very symmetric formula, okay? And you can, but this here works the same way. Like T-duality is this is we need to produce this in pairs. We need to start with a manifold, comma with class, and we have a lot of freedom to choose this H flux, and you can control the dual manifold. Okay. Okay, this is our first observation. But now we would like to go further. Okay, and now we use the symmetries. The first is duality, and now symmetry. Because how you can put your hands in this manifold? Okay? Because it's exotic manifold, but can we put geometric structures in this? Okay. And that is a very remarkable work to study symmetries or group actions on exotic manifolds. It's due to Grama and Meyer. The two Grama and Meyer, I guess, put the first example of curvatures on the exotic spheres, prove that some exotic spheres have positive curvature. Non-negative, sorry. Just for the guys from positive curvature is open. Okay. And this section, this construction, are based on work of several people like the Grama, Meyer, Duran as a student from Grama, Rigas was a Greek professor in UNICAMP, Esperança as a student from Duran, is my colleague in same class of PhD, and Kavanagh is present here. But I mixed these works and just for presentation. And the main idea is consider two actions, they commute. Okay, and we can capture some symmetries from the different action, and we glue these pieces. But the gluing is given by the transition functions of this bundle. And this will produce the exoticity, and actually we have additional group action to consider this space. I put this more careful. The main ingredient will be this diagram here, is P. We have two projections. Okay, and the two actions, dot and the star. And then just for simplify, we put this notation. And this is we call the GG bundle. And we assume that both actions commute. And if you consider the G times identity as a star action, and then another with the principal action, pi. And we denote the star action just for juxtaposition from the right and left on the computation. And the star action commute with the principal action, and it descends to the G action on M. Okay, and this makes the pi equivariant. And this is how we preserve the fibers, and you can make another action. And if I pick R in G, fixed by X, and for every fiber, point in the fiber, we are preserved also. And that exists a unique S, such that this RPS is fixed also. And we denote this G times GP, and this is the isotopy group. And we are imposed that this action to be free. Okay. And how this works in the practice is, as I told you, this is manifold are just pick subsets of the manifold, and we consider the bijections on this subset, and they satisfy some cocycle condition. And our new manifold are gluing these pieces, okay, for this manifold. And the gluing is given by this relation. We pick a point in the domain in image and the glue together. And we are in testing. We can pick this manifold covered by the opening of the structure bundle. The bundle we can cover that satisfies this relation, the cocycle relation of the bundle. And we are just this. We build the bundle, but not gluing by this transition function of the bundle, but we put some twist in this function. And then the new object provided by this F, some union of this subset, is a manifold locally resembles the manifold N, but that is global nature, it's a different global nature. Then this is the more simplified picture. You pick the bundle, you have some cover for describe the bundle, the open cover of the base manifold. We have some transition function, but now we twist this transition function for another action we call star action. And this is, as I told you, pick a collection, picking a collection of this transition function satisfies the cocycle condition, and we can define global maps using this representation theory, and then this is the most useful for us. And if we start with P principal bundle associated to the star collection, this is a cover. Then P admits a new action such that this is free and commute with the principal action. And then the quotient is a G manifold, G equivalently diffeomorphic to this new set, where the G action is restricted to G on M, and gluing this by this adjoint map described by here. This is how we produce, start with one manifold, and the two actions we can produce another manifold. And we can put the Grama exotic spheres in this language. Grama not use this setup, but this was proposed by Duran. And we consider this compactly group S2, and the 2x2 matrix with patterns. And then we consider normal conjugation, multiplication, and all. And they pick this action, Q on the right, is just multiply the second column. And then the start action is a conjugation on the first column. And if you pick this first action, you just consider the orbit space is just the usual sphere. But now you apply another action that commutes with the first, this action on the left, and then the orbit space in this case will be this 7 spheres, but this is a homotopy sphere. It's homeomorphic, but not diffeomorphic to this manifold. But now we have a lot of structure here, because now we have groups, submersions. We can use some, for instance, the properties of the curvature of submersions, like the formula from the Riemannian submersion, and we can estimate curvatures, etc. Comes from this option. Okay. And now, for instance, we can put the Milnor manifolds in this setup. We can put Milnor manifold in this language of the two actions that commute and pick different actions and different orbit space. And just for recall, the Milnor manifold are these two spaces glued by some functions. Okay? And we denote Pn this 0, n, and or the different is equivalent to minus n comma 0. And that this Pn is a principal bundle over S4. In fact, this is a result. This is a principal if and only if the Pn, this Pn are the unique Milnor bundles, principal Milnor bundles. All the other are not principal. And we consider this action. This is very related to the Grama construction. This is just an abstraction. We consider the two actions. One is multiplied by on the right, and the other is a conjugation. And this is just a remark. The Milnor bundle can realize it as this star diagram. Okay, you can realize this. And now we can put the two concepts together. The star diagram giving rise to the principal spherical duality and vice versa. This is now our theorem. If I start with the star diagram, I can produce in a spherical T-dual, and vice versa. If I have some T-dual, spherical T-dual manifold, I can produce the star diagram. And now we can use a lot of feats of the group action, the symmetries, to study dual manifold or spherical dual manifold. As proceeded by, for instance, Grama, they make Riemannian geometry by using the group action, the symmetries, because we can put our hands in the some exotic manifold. We can access this by symmetries, for instance. And we have this remark. T-dual and the star diagrams are equivalent in this language. For this this family of bundles. And then let me give some examples. If I start with this principal bundle, and then the dual we already know because we proved this formula. And these families, M11 is a diffeomorphic to unitary tangent space of S4. And we can realize this family as an infinite family of the spherical T-dual. This is a little bit more general because this equivalence is for spherical duality and star diagram, not necessarily for just spheres. For instance, this T1 of S4 is not a sphere. It's a unitary bundle of S4. But this is already know. This space admits exotic structure. This is what for Grove and Ziller. And we can produce this exoticity here by T-dual manifold. And we can put the Grama construction in our language now as a T-dual. And we can also go further and consider exotic spheres in the 8th dimension. This is just to look this action on this space. They multiply by left here, and they keep the first coordinate. And we have these functions for SH to S7 given by this expression. And this function is equivalent with respect to this action, this equation, and the action of the Grama sphere on S7. And we can just have a function that is equivalent with the two actions. And we can put this S7 as a boundary of the disk in 8th dimension. It glues this. And this will produce the exotic sphere sigma H. And we remark that it's just two classes of the diffeomorphism in the 8th dimension. And we have this diagram also. We can just not restrict yourself to 7th dimension. You can go further. You can produce 8th dimensional example. And this is still just tell us if we can pull back diagrams, and then we can make geometry in fact. Okay, we can consider geometric structures in the one side. I can pull back this geometric structure to the other side. This is really important. And then now we go to the last topic. This is the homotopy Hopf manifold. And then just to recall, we have the Hopf manifold is a odd dimensional spheres times S1. It's a complex, no simplicity, etc. There's a lot of well-known properties. It's a locally conforming Keller, etc., etc. But let us fix n is equal to 1 less n, and they consider this Milnor bundle. This is the homeomorphic to the 7 sphere. And we'd like to investigate the complex structures on this space. Now we have a homotopy sphere, 7 dimension, cross S1. Okay. And we'd like to understand what happens when we change n. And complex structure on this space was detected by Briscorn and Van den Ven. They proved, oh, some of this space admit complex structure. But we call this 8 homotopy Hopf manifolds. And we can use our technique and produce this star diagram. We have some explicit actions here. We have some explicit actions, and then we can adapt here the total space for the 8 dimension. And we have some general result here. And we are using all machinery we are developing. But if you admit a D-invariant complex structure, if and only if the dual, the spherical dual, also admits. And in this case, if we start with the Hopf, the usual Hopf admits a complex structure, the homotopy Hopf will also admit a complex structure. But now we have actions. And we have action, we can put hand and make some computations go further than big storm. Because big storm is just admit or not admit, and like mirrors, detect how to detect this. And we can also prove this. If the one side satisfies the Del-Bar lemma, the other side will also satisfy the Del-Bar lemma. And then we can compute this, at least in this example, the odd numbers and for the complex structure in the Hopf, usual Hopf, and the dual Hopf, not mirror. This is a very explicit computation. And you have this, the duality, you have the symmetries, you can look at the symmetries of the Hodge diamond. Actually, the usual, the same way like the usual T-duality, etc. And the main idea here is the spherical T-duality permute in the Hodge diamonds, and they produce some symmetries in the Hodge diamond. If you remember the beginning of these dualities and symmetries, actually study symmetries in the Hodge diamond of the manifold. And the same happens here. And in particular, we use this T-duality to determine when the complex structure on exotic Hopf manifolds are non-equivalent. And this give answer to the question proposed by Briscorn and Van den Ven. Actually, in the paper of the Briscorn and Van den Ven, this left this question to, need to investigate more because just detect complex structure on this space, on this exotic space, but not go further. And here we can detect it by the Hodge number. We can also compare this is a complex structure on this exotic space. Okay, thank you.